based on the conservation of energy, we have to be careful how to fractionalize, how to find another kernel. Yes, another question? Can you hear me?
Professor, I think many questions has been discussed. We have time limitations, time constraints are there because the next session is about to start. So we thank you, Professor, for your valuable time and the content which you present really very informative, valuable for all the participants.
Yeah. Thank you very much, and I am sorry that I was unable to explain, to present replies to all of your nice questions. Thank you very much for inviting me, and I hope.
And once again, thank you very much. And the certificate is proudly awarded to our eminent resource person for this session, Professor Dumitru Buliano.
Very much. Thank you very much.
Thank you, dear Professor, for your once again valuable time. Very much. Now it is time to start next session. I would like to invite Professor Satabir. Please start the next session.
Thank you,
Professor
Professor
Satabir
Mir.
Singh.
Thank you, Professor Mir. Am I audible?
Sir, you are audible.
Yes. Thank you. Our next speaker is Professor Ajay Kumar Shukla. He is professor in Department of Mathematics and Humanities in SBNIT, Surat. Professor Shukla did his masters from Agra University, Agra, and MPhil and PhD from Aligarh Muslim University. The field of his interest is problems of analysis and Q theory. He has more than 22 years of teaching experience. Professor Shukla has guided 16 PhD students and several students are still working under his supervision. He has given invited talks in various institutions. His total publications are more than 85 in national and international repute. He is on the editorial board of 50 journals. Professor Shukla is a member of several professional academic bodies like American Math Society, Indian Math Society, Indian Society for Technical Education, Ramanujan Math Society, Society for Special Functions and Their Applications, the Indian Science Congress Association, Vigyan Parishad of India. He has organized several conferences. I request Professor Shukla to deliver his lecture.
Thank you, sir, for your nice introduction. And here I will discuss in the field of pRq function. My slide is visible? Hello?
Not yet, sir.
Now?
Now it is visible, sir.
Okay, sir. Thank you, sir. So now let us start. And here we discuss about some of the facts on the pRq function. And basically, this function, nothing as simple, the extension of your exponential series, Metcalfe function, and hypergeometric function. And here in this work, this basically we did this combining the Metcalfe function and hypergeometric series. And this work is basically totally done by my PhD student, Mr. Right now they are Dr. Rasna Desai and Ankit Pal. And first I will start this outline of this my talk is based on the introduction for an unit of integer representation of this R function. Basically, here we will use to say this is the R function. And generalized is generalized incomplete exponential series type R function. Generalized fractional Kerr operator involved in the R function and application of the R function. So here we work on a mathematical point of view. This is not what we got some results and we try to apply the pRq function. So first, in 1903, as you know, this is a well-known this function. This is called Mitchell-Leffler function, as defined as equation number 1. This is now, and if I put this here alpha equal to 1, so finally we can average at this exponential series. So this is simply, you can say this is the extension of this exponential series. And second on this function, I think the 1905, the generalization of this function, he introduced this parameter beta. Then introduced parameter beta, so this is defined as equation number 2. And if I put now here, suppose this beta equal to 1, so this reduces to our 1, equation number 1, that is your Mitchell-Leffler function. And if I change this value, this alpha is equal to 1, so we can say this is E alpha E1 comma 1, that is your exponential series. Later 1971, and in between basically so many mathematicians work on the Mitchell-Leffler function, different their interest point of the interest, express some use some discuss about some properties and this applicability of this function, and some very interesting results of this. But here, due to some lack of time, just I not consider all these results. So then after this function in 1971, this is given by Prabhakar. He introduced the three parameters, and that is defined like this equation number 3. This is E gamma this alpha beta. Ultimately we can write summation n equal to 0 to infinity. Gamma going to n alpha n plus beta and to z is to power n upon factorial n. So ultimately here this is extension of this Riemann functions, and finally we can easily obtain the Mitchell-Leffler function as well as the exponential series by putting some suitable value of alpha, beta, gamma. 1995, the Kilbas and Jaigo gave another generalization of the Mitchell-Leffler function. This is function known as the Kilbas-Jaigo Mitchell-Leffler type function. He defined this is equation number 4, and where the C naught this is C naught and C naught equal to 1 and Cn. This is given by this one as equation number 5, and there's some. We also impose some here. They also impose some conditions that is mentioned here. That's in 5. This is an empty product assumed to be 1. Alpha m are the real numbers and belongs to C, such that alpha greater than 0, m greater than 0, alpha im plus l plus 1 is not equal minus 1, minus 2, minus 3, like this so. And the wide extension class is a function which is Leffler time further introduced and studied by the Kriyakoa, and this class based on the look of the class, the Kilbas Kriyakoa approaches the consists multi-parameter analogous of E alpha beta z called multi-indices Mitchell-Leffler function, and the Mitchell-Leffler function to the two key parameter and define for alpha I belongs to R. This is for this alpha 1 square plus alpha 2 square plus alpha 3 square plus alpha dot alpha k square. And this is a Bj. This belongs to C. And here this is defined can be put in the form of this as equation number 6. If I put now k is equal to 1, k equal to 1 in this number 6, then coincide with the parameter which is Leffler function at given equation number 2. In 2007, myself and Jyotin Prajapati worked in this field and generalized this concept of Mitchell-Leffler function as well as Prabhakar function into equation number 7. And with this, by imposing all the conditions, this is all these conditions are mentioned below here. And 2009, the new generalization of the MATLAB function was defined by the Salim at the equation number 8. In 2009, this Srivastava and Tomovsky introduced and investigated the fractional calculus and integral operator which contain the following family of the generalized MATLAB function, and it's question number 9. And with these conditions, here this is alpha, beta, and gamma. This is belong to C with real alpha greater than maximum. This R and this R kappa minus 1 or kappa greater than 0. And next we have to come. This is for the generalized hypergeometric function. So basically, I would like to share my view here because for the newcomer, those who are interested to work on this. So if you go for the bottom of the work, and definitely you will get some new point of concept like suppose here we take left of function, then we do one parameter, then again ultimately we will have different every function, and this is your generalized hypergeometric function defined as you could define equation number 1. This is defined in equation number 10, equation number 10. And here we can put in the form the Poisson symbol of this. This is defined as equation number 11. And the generalized hypergeometric function satisfies the following integral representation that is given by the 90. This is given by the 12. And here we also give some concept of the generalized right hypergeometric function. This is the right hypergeometric function. If you compare with this generalized hypergeometric function. So if you put this pair in the form of this Poisson symbol, then we basically here that reduced removed this denominator parts and you like the results that is given in the equation number 13, and put in the condition for the would satisfy the condition that is given as this sigma j equal to 1 to q j minus sigma equal to 1 to p. This is ui, this is greater than minus 1. Okay, and this started, this is the right type function is this, then this can be represented as equation number 15. And here generalized capital differentiate function, this is defined as equation number 19. It satisfies the following convergence criteria that is mentioned below here. Now we discuss some definitions, some representation of the Laguerre and the Kornhauser polynomial that is defined here. This is 17. This is a Kornhauser polynomial given by the Kornhauser, and this is can be reduced to Laguerre polynomial by putting this is this parameter, this k is here. So if I put k is equal to 1, then this become Laguerre polynomial. Now we discussed this pRq function, or this is defined as the R function. So this R function is was introduced by my student Rachna Desai and myself, and this is further the work carried out by Dr. Alfipar. And this is introduced the function is defined like this, or we can say this is given as equation number 19. So first basically here, if you see these are your hypergeometric function. And if I take this one, it's a 1 upon this is gamma alpha n plus beta, and this is z raised to power n upon factorial n. The ultimately due to this one, you can say this is a type of your this MATLAB function, hypergeometric function. That's combining these two, and finally we get the result. This is the 19. And right now we are also trying to find out the differential equation for this study function. If we succeed, this will definitely very good for us, for the study, for the function as well as the differential equation. And here, these are the convergence condition of this function. This is defined here. These are the convergence condition, and we can put some if I repeat this, alpha is equal to 1, beta is equal to 1, this u1 is equal to 1 like this, so ultimately we can get the generalized hypergeometric, where this is in the form of the p minus 1 and f2. And similarly, this function, this is giving to the 90. If I put now p is equal to 1, q is equal to 1, u1 is equal to 1, so this function becomes one or not function and defined like this. This is E alpha beta, and this is the generalized Mitchell-Leffler function. And here we get some use of this function for obtaining some new results like this. So first now I use the Fourier transform representation of this function. So this is defined like this. So here we basically pRq function alpha beta we are putting over here. This is nothing else simple. You can say this is symbolic representation of the function in different manner. That is given as equation number 20. Equation number 20, this is for integer. So that you can say this is the integer representation of this pRq function. Now, because of this representation, definitely they play with basic property of your special function. Function, if we say this is a integer property, there is integer property of this function, or integer satisfy this condition, or we can represent in the form of some integer representations function, and then we keep a good chance we call this is a special function. And here we satisfy the following representation that is defined to you, and this is equation number 21. Okay, and this is the all the condition. This is here. So here the first we have defined this one. This is given by this, and so finally we can get the result of this. This is given into this form. I satisfy the form distributional representation of this function. That is the defined equation number 22, and this distributive transform, this is representation defined at 22 only meaningful when it is specified in a product with a good and good and the relate to the space of the good function for the further reading of the good function equation number 36. J is equal to 0 and 2022, this function reduces to Fourier transform and distributional representation of the gamma function. Then defined as 23rd and sorry 23 and 24. So if I put the corresponding values, it ultimately you can get some results like this. So it is given results in the form of 25 as well as this is the form number, this is the form as a 26. And here, for the case 3, if I take the alpha is equal to 1 and beta is equal to 1, and u1 equal to u is equal to 1, then this reduces to, this is your 27. And 27, and this is your 28. With the following condition, this is lambda greater than 0. Next, we discussed this case 4. This is our case 4. We define as if we take this u1, u2, u3, u4 up to up, and this is equal to 1. And v1, v2, so v1, v2, v3, v2, ultimately that can be right now. This is your qm, this equal to 1. Then this is the Fourier transformation and distribution transformation 3 parameter that is defined in the equation number 29. This and this is equation number 30. Equation number 30. So this is equation number 31. Next, I would like to say this is theorem. By utilizing the possible identity of the Fourier transform, following these are all true for the R function. So here this is defined at 32, and here these parameters are given. This is this implies the sequence of the parameter, given into this like B of beta for alpha, and beta plus alpha, beta plus 1 divided by alpha, and dot dot beta plus alpha minus 1 divided by alpha. And also we can set lambda plus delta greater than 0, Bp less than equal to Q plus alpha, and this is which is less than S, R is less than S, okay? And this is your mode of Z is equal to this is mode of Z, is less than 1, P equal to Q plus alpha, and omega equal to, those are less than 1, if R equal to S plus A, alpha, sorry. And next theorem, this is given, so corollary of the theorem, this can be represented in the form of the equation number 33. This is again the same pattern, same like our results, previous result. And next now here, this is corollary 16. And also, if I put this delta is equal to lambda, then we can get this is 34. Question number 17, this is a 1.7. 1.7, this is by putting some suitable value of alpha, beta, and UP and CR. This is to question, now this is 35. This is 35. And this is a corollary 1.8. This is alpha is equal to 1, beta is equal to 1, and taking only two numerator parameter, this u1 is equal to u and u2 is equal to 1, and one denominator parameter v1 is equal to v and c1 is equal to c, c2 is equal to 1, d1 is equal to d. So theorem 1.4 reduces to the integral product of the two Gauss hypergeometric series. This is a function as defined. This is as defined the reference, that is 3. And this can be represented as a equation. This is as equation number 36 by using the Fourier hypergeometric series like this. And now here we can give some an application to the Mitters-Leffler function. So this one, this is defined, this is given to you, this is, and this can be represented as equation number 37. So simple, we can say this is for result, and then they will return true for the Mitters-Leffler function. It basically here we try to implement the Mitters-Leffler function, and that also gives the result 37. And similarly, we can obtain this equation number, this is result number 38. And here we give some this Euler type integral representation of this function. And this function defined, this is real, this W greater than real, V greater than 0, and 3 alpha 3R2. 3R2 basically when we consider pRq, it means this is pRq is equal to 3 and Q is equal to 2, and this is your alpha and beta, and other terms are here inside this this bracket. And this finally we can write down, that is equation number 37. So this is basically equation 37. It means here we can see, one can easily see that we also got this representation. This is nothing simple Mitters-Leffler function. So we try to club this result with the Mitters-Leffler function also. And earlier, basically, if you see, this is the origin, basically the function originating from the combination of the Mitters-Leffler function and the hypergeometric series. And here, this can see, you can see here, this is now equation number 40. This can be used some. Hello? 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 Naturally. Hello? Hello? There's some disturbance actually. Please, there is some disturbance. So this is 1.4 is this, and we can also write. Next, we can put in theorem that's found in this theorem, this function, the pRq function. So you have pRq with respect to 3R2. So this can be obviously compound in the form of the Cohen-Hauser polynomial of equation 34 obtaining K 34. This is this is 41. This is the Cohen-Hauser polynomial, and we also define it as different 34. And by putting some suitable value of the m, this can be represented in the form of the Legge polynomial. This is given as equation number 42. So I think this all of you are familiar with this Legge polynomials, and this is so this k is beta minus 1. This is your Legge polynomial. This is. And now next one is this is the fourth theorem, this Euler type integral representation of this pRq function. This is given as equation, this is 43. And these are the Poisson symbol. And we can also, by putting some alpha is equal to 1, a very special case, then ultimately here, this is the function, this is enable to reduce the confidence hypergeometric function. So basically, this is one F1 series. So this can be easily reduced to one F1 series. And next, we'd like to give this theorem. So again, this theorem is also in the form of the theorem, and this is a type of representation of this function. This is q plus 1 q. So ultimately here our p is replaced by the q plus 1. So this can be reduced. This can be reduced to this equation 45, and this is nothing else simple. This is a we can say the Kornhauser polynomial. This one is Kornhauser polynomial. And now here we can also, this can be equation can be easily reduced to different type of integral representation. Okay, so this is the number 46. Next, we can take the 17 equation. This is the theorem 1.171. So basically, this is taken from the thesis. So this is given in the form of the thesis. So this is equation number 47, and this work is published in this journal. So next one is here. Here we discuss some generalized incomplete exponential type R function. So here we will definitely like to put this in the form of the incomplete hypergeometric function, and that is this defined as 38, 49, sorry 48, 49, and this is 50. This is your 50. And next now here we can put in the form of this Poisson symbol, gamma function, and so a type of the Poisson symbol we can see, and this can be also satisfy this result. This is given by this is the W semicolon X, this one and this one. So in complete, this is your gamma function. So finally, next we arrive to discuss some uh, result. This is your omega going to k, and this can be represented to like this is your equation number 51. Here we take some, this is incomplete exponential or function we discuss, and this is totally based on the work of the Chaudhary and Kadir. And Chaudhary and Kadir basically this work, and he motivated to study incomplete gamma function, and they have given incomplete exponential function as mentioned below. So this is the first function. This is given by this. This is equation number 35. So this is into this form is e xt here. This is the one function. U is there. So finally we can write equation number 55. Next, now this convert equation number 56. So basically, there's nothing else simple. If you see, this is from here only. So then this one is not only, so finally this gives to you this confirm. And combining this result, so ultimately you will get some exponents. This is exponential series, this is e raised to power t. So this can be given as equation number 57. And this is this is very interesting. Regarding to represent complete exponential important our study. So we use this results in many of our research work and this paper. This is given as this is 58, and next one is the 59, like this, and now here 48, or this is your 58 is this, and this is 59, this is 60, this is 61. So it means it can be also the represent in form of the incomplete exponential function. This is your 62 is this. And here, if I put this value, corresponding value, then you will get this x1 beta, and this is the mu, and this finally this can be represented as equation number 63. Equation number 63. Now, if we have suppose 0 e0, this is a one function is this, so it means here we can write in the form of this. Okay. So basically write to this is the e0 e0 to x1, x is this, 1 is this, beta is this, and this is only this now here. So this can be put into this form. This is equation number for this is 64. So basically here the relation 62 shows it is sufficient to prove the certain property of the incomplete exponential series, exponential pRq function, you can say. So this is a function. So here we can give some concept basically here. We are motivated to work and discuss some concepts, some fundamental results. Those who are interested then they can go ahead. And here this is now the first integral representation, to one time of the representation of this, sorry, one incomplete representation that given as equation number 65. And here we can also to put some corresponding values of this alpha and beta, P and Q. Then this is equal to alpha equal to 1, beta is equal to C1, and this is a P is equal to 1, Q is equal to 0, U1 is equal to A. Like this, ultimately we can get this one. So 1 E0 or 0 now can be written into this form. And here we give some second integral representation of this function. This is given as equation number 66. And next one is this is for the generalized exponential function. We have the following derivative formula. So it means we have to try to club this club, and finally let us see what happened. And this is a basically derivative of this. So there is any derivative of this. So this when we take the any derivative, this can be given into this form. So it with this portion, this can be represented the course of the time. And this is 67. And next, this our function, we have following derivative. So here, this derivative is this. So this is nothing, a simple corollary. And here we can use some partial derivative of this function as given equation number 68 and 69. And the further, this is your the estimation of 2E1 function. And this can be represented like this. So basically, even nothing, basically here, again, we put it in this form. If you see the definition, so ultimately you will get entered into the result and will systematically. So this is given into this form, this is equation number 70. And here we can approach for obtaining this like for the recurrent relation. So this is the recurrent relation. This is defined at equation number 71. And after the function, we give some this function for the addition type, function, like our variable, this given variable, suppose x plus x, y given, then we consider x plus y, like this now. So here, this is now we have to generalize into form of the two variable, and like this, whether then we have to see whether these two are satisfy the condition of the summation or multiplication, whatever it may be. So that is defined, or this is the addition formula or formula of the two arguments. This is valid like this. And next, now this is for the generalized incomplete exponential series. This is defined as equation number 71. This is equation number 73. Next, now the generalized incomplete exponential. This PEQ, A column, sorry, A, this is X, this is your A, and this is B, and your B function. We have the following integration defined as
Sir, you are not audible.
I think this is connectivity problem, net problem.
Sir, please carry on.
Slide also not more. I think there is some problem in net connectivity. Professor Merchant. Professor Merchant.
Yes, sir. Audible. You are audible.
Yes.
Please carry on.
I think this is some problem of the
Yes.
net. Okay. Connectivity problem. That's why
Okay.
the screen also not move. Okay. I talk to you. Wait for a few minutes. Professor Shukla join again due to the poor connectivity. Wait for a few minutes. Hello, Merchant. Professor Shukla will join due to the problem of poor connectivity. Okay. As soon as possible, he will join again.
Dear participant, please wait for a few minutes. Our mentor will rejoin the meeting. There are some participants from on the YouTube. They are attending through live streaming and asking about the content which are presented in these sessions. So don't worry about the content. We will share all the content according to sessions on your registered email address. Okay, and also along with the cloud recording is there. We will provide all the cloud recording link on your email address. And along with the, each session, each day, we will provide you the feedback link on your email address, and it is mandatory for all the participants to submit feedback link. Okay. So if you have any query, and after that, you can submit your question in your chat box. And also there will be some questions in the feedback form. You can submit your questions there.
Hello.
We will target.
Sir, okay, sir. Please share the screen.
Okay.
Screen is still not visible. Please share the screen.
Okay. Okay. Let us see.
Okay.
Problem. Is it visible?
Yes, sir, it is
Yes,
fine.
yes,
That is
sir,
fine.
Yes, yes,
Okay,
sir, fine.
okay. Sorry, extremely sorry. Today, really, this is very. So we were at this equation number 84 as well 85, and we can. Next, we will discuss about some this application point of view. This is application to groundwater pumping modeling. So here they use this term and this putting into form of the this pRq function. So this is m delta eta. This is defined in 86. Next one is m star eta. This is defined by 87, and this is basically this is the quantity arises in this. You can say the respect to groundwater pumping modeling used in 1964, and further this one. So this can be represented into for the 2000. The 2005. The traffic gave the algebraic representation of this function defined like this. This is equation number 88, and further this can be using the concept of this the gamma function, incomplete gamma function. You can say this is your 89. And here we can also write this into form of this. Finally, we can arrive at this generalized incomplete exponential function defined as by the 16. This is the figure. So, defined like this. This is equation number 60 is this. Equation number 60 is this. Then this is now here we can use this into probability theory, and theory. This is defined some Janardhan et al. This is the study stochastic process, and this through the probability mass function. This is defined as the 91, and this 92 is this now here, and further we can say this is a 93, 94, and here, so here we give some theorem of this. This can be represented. This is let x is greater than equal to 0 with the continuous time Markov chain with the x naught is equal to 0, and this is transition the probability as in 93 then 94 can be derived in the terms of generalized incomplete exponential function h. This is the 95. And here we also use this function, the non-central chi-square distribution. And this can be, one can see this, the form of this is your this 97. And basically there's nothing simple. These are the Bessel functions. These are Bessel functions. And so finally, this can be easily converted into zero for hypergeometric series. And here, this can be written. And finally, here we can also put in the form of the generalized incomplete exponential function. And this work is published with this is Georgian Mathematics Journal. Recently, it's published 2022. And here, generalized fractional operator involved with our function. Here, with simple, basically we try to use this operators, well-known operator. Those who are working in this field. This is the form of the 100, and this is your 100-01. And this and with this using this the conditions the boundness as defined equation 109. And further we have to use this lemma 103, and then for this is a beautiful result of the Hilford. This is a claimed remark application of generalized the fractional operator and generalized Riemann the will fractional derivative operator defined by this. And so this is a different Hilford derivative defined as 104. This is given like this. And further, this is nothing simple. One can see this is Laplace transform like this. So here, and further, we discussed this is this is P transform. So that is defined like this. This is defined as 106. So basically, this is nothing as simple as you can say the extension of this Laplace transform, and this is if the condition is this here. If this is the 1 plus mu minus 1 into s and whole raised to power minus t upon mu minus 1 equal to e raised to power minus st. Then x tends to 1, then it reduces to the Laplace transform ft. So this is 107. This is defined like this. And next now here, this is this lemma and the power in the form of the power function. This is 108. And here we discuss some main result of our work with using all this transform. This is the form of this 109, 110, and this is gives a theorem. This can be represented in the form of this this pRq function. So ultimately, the pRq function. So finally, this gives the result 111. And here, this is if I use a derivative of this one. So finally, this is 112, and this is 113. And we also give some recurrent relation of these functions. Actually, looking at the time constants, I'm going fast. So this is given like this. So this is for our the recurrent relation. This is 114, and this is 114, and this is 115. And here we use the composition of this Riemann function operator and the Hilford function derivative operator with the F function and the form of hello. This is the result. This is 116, 117, and 118. And here, next one is we also use the operator associated with the R function, 119. And this gives you the remark of this basically in the light of the result is 30. This one can observe up equal to 0, then 10119 can be reduced to this Riemann level or fractional integral operator. This is at 100 operator this, and this is the 120 is this one. So finally, now we give the theorem 1.14. This is in the form of this. So basically, nothing simple to here. This theorem we give some condition. This is boundness of this by using this operator, and this in the form of the 121 as well as 122. This is some remaining part of this, and this is one lemma here. This is 125, and this is here effectively our function is this, and operator with this lemma. So finally, we can get this result. This is 125, and theorem share here, and I think I would like to take opportunity to go faster. So that this is next we use some differential type. This is your first we take some preposition. Then we will use this one in our work. So this is as mentioned. This is 134. This one and further you can say here this is your following differential equation. This is 135. And this is 130 conditions are given here the 133, 130, 135, 136, 137. And this is one fractional differential equation. This is a 138. And conditions is this. So finally, we can obtain the result into this form. This is 140. Similarly, here, because the next differential equation in the form of 141. Conditions given 142. This gives the result at 143, where the constants are also mentioned here, the C3 and C4. So already the order is 4. So ultimately, here, so we can convert this into, or this is a C3 is this, and C4 into the C3 and C4. Sorry, C3 C4. Sorry. And this work is also published this, with Iranian Journal of Science Technology. And this is a National Academy of Science letters. And here we give some this Natoli work. We try to correlate our work with Natoli work. This is as equation 144 and 144. This is basically if you see this this is the water integral differential equation. This is 144, and Next one is this is a 144. This is using this RL fraction integral and derivative operator. This is given into this form. And it's 147. This is free electron laser. This is defined. This is considered like this, and that gives into this form. So finally, here we can get the result into this form, and this can be repeated the pRq function. Like so ultimately, we can convert all the value. This is by using the operator, so we can easily get this pRq function. And this one of the result is here. This is a generalized free electron laser equation defined as 153, and further this can be obtained like this. So basically, this is the development of this function. This is work of this. So this is some publication, this especially based on the pRq function, and future work, those who are interested and they can think about this work, and for and Q analog maybe they are possible. And here we can use a matrix analog of this function. And these are the references that have been used by us. This is given by this. So thank you so much. So really, I am very sorry for this interruption. I think.
Thank you, sir, for your valuable talk. I ask from the participant if you have any question. You are permitted to unmute yourself and you can ask your question. Please feel free to ask your question.
Question then ask. I think one question. Andrew,
Hello. Hello.
please, please.
Please.
Okay. No question from the participant. Okay, sir. Thank you. Thank you, sir, for your nice informative talk and spare your valuable time to us. Request to Professor Merchant. Okay, present momento to Shukla sir, please. Professor Merchant. Present momento to Shukla sir. Okay, very good.
Thank you. Thank you, Merchantji. Thank you so much. Really, you did this very wonderful job, and as still doing, not did, I think you are doing, currently is going on. Very wonderful job, I think. This is a good thing for the newcomer, those who are interested, those just completed the master degree and interested too for the research work in the study, and also this your work will definitely encourage the newcomer and also keep the interest in the special function. Thank you so much. Thank you so much, Max. Please.
Thank you, dear Professor, for your valuable time and informative thought for all the participants. And I hope the content which are presented in this session are really very valuable and informative to all the participants. Some participants were trying to asking some questions, but due to, I think, network problem from their side, they are not able to unmute. But still, we will share the content which presented in this session. And also there will be feedback form, and they can submit their questions in the feedback form. And after this training workshop, we will organize one more training workshop, which will be based on the problems and questions gathered in the feedback. and this will be after the interval of 2 or 3 months with the same collaboration from his side.
Right.
Thank you, dear Professor, once again for your valuable time and thoughts which are presented in this session.
Thank you, Maharji. Thank you so much.
Maharji, we are taking the recording. Hello.
Hello?
Yeah, we are taking the recording, na, Maharji?
Yes, we have the recording.
Yes.
So if any participant has any doubt, they can go through the recording as well, and they can mail the speaker also. So that is also another benefit. Maybe their problem in the real time in online. So they can go through the recording, and if they have any doubt also, they can directly write to the speaker also.
This session is over, and we will resume the meeting after 10 minutes for the next session. We have about 7 minutes, and after the 7 minutes, we will resume the last technical session. That will be start at 1:30.
45 to 3:45, I think.
Yes,
Please,
yes.
Merchant, please confirm that it is start from 1:45 to 3:45. 1:45 as per our this schedule. It is mentioned that 1:45.
Okay, sir, no problem. Dear participant, we will resume the meeting after about 20 minutes.
20 minutes, yes. 20 minutes.
Yes.
Okay, this is good. Okay.
To all.